Kia ora Ben, Tosif and Snehal and 12MCA if you're out there watching. I'm going to start doing some past paper questions from stats now that we're getting our way through that part of the course. This is a question about the normal distribution. Now it's quite a big question. It's 9 marks out of 50. And at first glance it looks pretty hard, but both of these all come down to the same things with normal distributions, which is how do we standardize and solve some equations using Z. So in the first one, we're told that the lengths of the leaves of a particular type of tree are modelled by a normal distribution. A scientist measures the lengths of a random sample of 500 leaves from this type of tree and finds that 42 are less than 4 centimetres long and 100 are more than 10 centimetres long. So that's all we've got, right? We haven't got the mean and we haven't got the standard deviation. What we have to do from that information is we have to estimate both the mean and the standard deviation of the lengths of leaves from this type of tree. So if we've got 42 out of 500, that represents, let's see what that is, that's 0.084. And we can say that the probability that a leaf, X, is less than 4 centimetres is roughly equal to that number. And then we can do the same thing with the 100 leaves that are more than 10 centimetres long. So 100 out of 500 means 20% or 0.2 of the leaves are greater than 10. So that's 0.2. So we've got these two probabilities and we have to figure out mu and sigma. First thing that we're going to do is to draw a picture, and you can see that this is 5 marks, so there is quite a bit of work in here. This also comes up in the level 2 probability paper, and if you're lucky enough to get this, it is sometimes an excellence question. So if we draw a picture here, oh, we don't want that, let's get rid of that. Draw a normal distribution picture, like this. This is X, this is the leaf length. We don't know what mu is, and we don't know what sigma is. But we can colour in here. We know that about 8% or 8.4% is below 4. And at the top end, we've got 20% or 0.2 greater than 10. So what we're going to do now is find two z-scores, and then we've got two unknowns to solve for. So you should be on happy simultaneous equation territory because that's what we're about to do. Right, so looking in the tables, and we have to get really good at these tables, we'll do this top end one first. So what's the z value that cuts off 0.2 here? Well, that means I've got to have 0.8 here. So I'm looking to find this. The probability that z is less than little z is equal to 0.8. Now the big Z, by the way, is when we're saying this is the random variable, right? And this is a specific value. So we're trying to find what is that specific value that's going to cut off 80% here. And we go to our table. Where's the table gone? Here we go. Nope, that's the wrong one. Right, I can't use my critical values because it doesn't have a number for 0.8, right? It's got 0.75 and 0.9. So I have to look through the table, and I'm scanning through here to find 0.8. And it's pretty close here. So 0.842 will do it, right? So I've got let's just look at how that works one more time. This is pretty close to 0.8, but I need to add on that little 5. So it's going to be 0.842. That's my Z value there. Okay, so that little z is equal to 0.842. So that's that one. Now we do the same thing for this end. This is a little bit more work just with how the tables go. So if we've got 0.084 here, that means we've got 0.916 here. In the table, what I'm going to look up is what that number is to give me 0.916, and then I'm going to take the negative of that value and put it down here. So we're solving the probability that z is less than z is equal to 0.916. Going back to my table again gives me little z is equal to, so we want 0.916. Definitely have to wade through the table for this one. So here's 0.916 Up here, what am I after? 916, 913, 915 here. So it's between these two. So it's going to be 1.378, right? And I'm doing that because that's 0.9147. And then I need to add on those 13 extras. Okay, so the value we've got here is going to be 1.378. 1.378. So that's the value there, but I want the negative of that value, so that's negative 1.378. And hopefully you can see that if you're drawing the pictures here, keeping track of the negatives is actually not too bad, right? But if you don't, then you're going to come unstuck pretty fast. What do we have to solve now? Well, we know that to go between x and z, we've got this formula. We're going to substitute in two sets of values. The first one is for the leaves that are shorter than 4 centimeters. So we have 4 minus mu over sigma is equal to negative 1.378. And we have 10 minus mu over sigma is equal to 0.842. I'm already up to 6 minutes and I haven't even started the second question. So what do I get here? Well, it's pretty intuitive, right? So we get 4 take away mu is equal to this. So this is measuring the gap between 4 and the mean, and we're saying that it's negative 1 point blah blah standard deviations below the mean. And here we get 10 minus mu is equal to 0.842 sigma. Obviously, lots of ways that you can solve simultaneously here, but what I've done is just this. So 4 plus 1.378 sigma is equal to mu. So that's rearranging that one. And over here, I get 10 minus 0.842 sigma is equal to mu. And that's here, right? So we've got two equations that we're going to solve. We're eliminating mu. We've got 4 plus 1.378 sigma is equal to 10 minus 0.842 sigma. It's not conceptually difficult, but it is mucky. So 1.378 plus 0.842 sigma is equal to 10, take away 4. Sigma will equal 6 over that number there, which is 2.22. Sigma is equal to 2.70 to 3 significant figures. I think that's what they asked us for. And from here, we're going to substitute it back in, and we can get mu into here. Right, so mu is equal to 4 plus 2.70 times 1.378 because of the formula that I worked out. And that gives me a mu value of 7.72 to 3 significant figures. Right. Now, before we go any further, we should just go back up to the graph and see if that all makes sense. So let's have a look. Here's my initial picture. And it is worth doing it reasonably accurately. Let's put on our mu value here of 7.72. Does it look right? Well, it does, right? Because you can see that this is quite a small probability. First of all, 4 is less than that, so that's good. And 4 is 3 and a bit away. So that's chopping off 3.7 away, so that's chopping off a lot. Whereas the 10 here is only, I don't know, 2.3 away. So this is not as extreme a value, and that's why I've got more stuff above it in the tail, right? Whereas 4 is quite a long way away from the mean. Always worth doing that quickly at the end. So that's the first 5 marks, right? Let's see, find estimates for the mean and standard deviation. Yep, so that's good. Okay, the second part it also looks weird, but if you just draw some pictures, it's fine. The length of leaves of a different kind of tree have got this distribution, and again, we've got no numbers. We're just told there are 800 leaves being taken from this type of tree. Figure out how many of these leaves the scientists would expect to have lengths between 2 standard deviations below the mean and 2 standard deviations above the mean. So way back when we started the normal distribution, I think I probably told you basic facts about the normal were that I really have to turn that feature off here. So basic facts about the normal that I got taught when I was 15 and at school is that if you went one standard deviation either side of the mean, you covered roughly 68%. And then the next thing that we got taught, and we had to memorize these facts, right? So, which was actually kind of useful. It's one of those stupid facts from maths that I've always remembered. So there's 2 standard deviations either side of the mean was roughly 0.95 area in there. So we need to do that exactly, but that's what we're doing here. We're saying if we go, here's mu, and here's mu plus 2 sigma, and here's mu minus 2 sigma. And we need to figure out what percentage is in there. So we can very easily standardize that, right? Because we know standardizing is just how many standard deviations above the mean am I? That's what it's all about. So down here, here's my Z picture. This is 2, 0, and -2. Or if I wanted to go slowly, we're going to use x minus mu over theta, right? And the x value here is mu plus 2 theta minus mu over theta, which is just 2. So what do I have to do? Well, I just have to go to my table and figure out the phi of 2, right? So what probability is there of being below 2? So let's look at the table again. Luckily, I've put just enough in the table that it's there. So looking at the table, we get this, 0.9772. So this is saying that if I go, here's 2 theta above the mean, that all of that is 0.9772. So the probability of being above mu plus 2 theta is going to be 1 minus that, which leaves me with 0.0228, and it's symmetric. So the probability of being below that is equal to the same thing. Don't write the ditto marks, that looks really silly. And that means that the probability of being in between is going to be 1 minus that, which will be 1 minus 2 times 0.0228, which gives me 0.9544. So we've nearly finished the question, right? We've done all the hard probability stuff. We had how many leaves on the tree? Let's see. I think it was 800. Yep. So there were a random number of 800 leaves on the tree, and the scientists picked them. So how many did we think would have lengths in that range? Well, we've got the probability. We just need to go 800 times 0.9544. And we need to put some words. We'd expect leaves in this range. So that number works out to be 763.5 leaves. So about, I don't know, I'd say 764. The mark schedule said 763 or 764. Maybe we'll put both down. 764 or 763 leaves. They should accept that answer because all you're doing here is you're estimating, right? You had a probability that came from your first sample of leaves. So, you know, it's not going to be that precise, but I'd be happy if you wrote 764 or 763. Okay, so that's all for now. That question is quite a big one, and there's quite a lot of new, harder stuff in there on the normal distribution. So just keep on going with the 7A and 7B work, and I promise it will slowly get easier.